start by trying to motivate this. Okay, so we can sort of go back to the standard thing in information theory, which is the data processing inequality. So we have some quantum channel, we have two quantum states, they go through the channel, and then we say that they're harder to distinguish than they were when they came out. This is the data processing inequality for an arbitrary divergence. And we use this all the time, right? We use it to establish real converses, that sort of thing. But the problem is, normally when we use it, we have sort of states in mind, and so it's harder to attack these more general setups where you have a whole circuit, which we could think of as having many gates, which are a bunch of channels. And so if we want to capture data processing in this setting, we need something stronger than the data processing inequality, at least intuitively. And so this is where contraction coefficients come up, which Christoph talked about on Monday. And here the idea is that you're really capturing how much a given channel will contract any two arbitrary inputs. So it's a way of measuring how strong the data processing inequality is for a given channel. And the reason this is useful is because you can then sort of decompose thinking about this whole circuit, right? So I have 4 layers of a circuit with gates at each layer. I start by thinking about all of the layers being applied to the states, and then I take the contraction coefficient that's like peeling off the last layer, and I could peel off each layer over and over, and so then I just have a set of contraction coefficients and then the distinguishability at the start, right? And so this is really nice, but then we have this sort of clear problem, which is how do we compute these contraction coefficients, right? If we actually want to use these, then we have this question. And then sort of a secondary question that I think is very interesting is if I give you an ancillary register, which is noiseless, can I do more? Like, are there barriers that show up there? And so we ask what happens with the noiseless ancillary systems. And so there's certainly been progress in this, these directions. I can't list everything, but in terms of computing these things, Kia and Ruskay have this paper from 2016, and then Christoph has this earlier paper on quantum Doeblin coefficients, which is sort of the motivation for this work. And then Gao and Roget have this complete entropic inequalities paper, which introduces this sort of noise idea of the noiseless ancillary system, but not in the robust way that we look at it in this paper, I guess is fair to say. So the last thing we need to motivate this is, as I said, Christoph had introduced these quantum Doeblin coefficients last year, which motivates this. So let's sort of take an account of that to motivate the rest of the talk. So we can think about starting with the classical case, because it's always easier, I think, to think about the classical case before we jump into the quantum. We can take the total variation distance contraction coefficient, which with a little bit of work you can actually show is just distinguishing how distinct outputs will look for distinct inputs and maximizing over those. So that's actually kind of easy to evaluate, but you can still upper bound it by this quantity 1 minus alpha, where alpha is the Doeblin coefficient. And it has this very simple form where you look at all of the possible outputs and then you look at the least probable input according to the channel. And in the quantum case, it gets a little more complicated. So we take the trace distance contraction coefficient, which is the generalization of the total variation distance. And Ruskay has shown that, in fact, again, we have this idea that you're maximizing over distinct inputs and looking at their output. But the problem is this is not efficient to compute as far as we know. And in fact, there's supposed to be some upcoming work that will show this to be the case by the Fauzi group. And so we can instead try and do Doeblin coefficients. So doing the same idea that in the classical case, but now in the quantum setting. But here, in sort of the standard way that quantum stuff works, there are a whole set of Doeblin coefficients. We don't just have one in the same way that we see this in divergences and entropies. So there's the first one that was introduced by Wolf about a decade ago. Then there's another one that Christoph and Wolf considered. And then there's a third one that Christoph introduced. So we've got 3 quantum Doeblin coefficients already. And we would like to, but the important thing is that Christoph showed that 2 of them are efficient to compute. So now we have this theory of Doeblin coefficients that we don't really understand for the quantum setting, but we know that they're at least efficient to compute sometimes, so they can be used to handle these contraction coefficient settings with the large circuits. That's the idea, that's the hope. So what are we doing in this talk then? We're going to first operationally unify a family of quantum Doeblin coefficients. This is going to give us sort of an understanding of why we have multiple ones in the quantum setting. Then we're going to show that one of them is an efficiently computable upper bound on a complete contraction coefficient. So this is handling this noiseless ancillary register problem I mentioned earlier. And then I'll show you how to apply this to some specific instances of noisy quantum information processing, so showing limits on this. So that's the idea. So, and we'll just go in this order. Yeah? Okay. So let's start by unifying these contraction coefficients. So we could start sort of by thinking in terms of hierarchy. So one way of rewriting the classical Doeblin coefficient is this optimization over positive vectors, which is kind of gross but is a linear program. We can make it look a little bit cleaner, I'd say, by using the Choi formalism. So if I take a channel and I use the Choi isomorphism, then I can rewrite this optimization as just maximizing over the positive semi-definite operators, where we have this sort of relation between the Choi operator of W that we're interested in and this object, which you can think of as the Choi operator of a replacer channel if you want to. And this is the normal positive semi-definite ordering. And so this is what I would label as alpha plus. And then we have the quantum Doeblin coefficient, which you really want to think of as the key one in this sort of framework, as we'll talk about today. And then we have the third one, which is the one introduced by Wolf, where all we've done is we've changed the Loner ordering to the cone ordering in terms of the dual of the separable cone. So what do we actually see here? We see we've got three Doeblin coefficients for quantum channels, and they are increasing in value because the first one we restrict to maximizing over positive semi-definite operators, then we go to Hermitian operators, and then we relax the cone ordering, right? So they're larger than each other. We want to think about what that means. In the case of just changing the cone ordering, this is sort of how we're going to unify these operationally. This is building on some work by me and co-authors during my PhD work. And so I'm not going to go too much into the technical way of doing this. I'm just going to explain sort of operationally how these things get unified. Okay, so now if we have this unification sort of in terms of optimization, we want it in terms of an operational idea. The operational idea we'll use is noisy state exclusion. So we go back to the Doeblin coefficient for a classical channel, which is the summing over outputs and then looking at the least probable input. And we can think of this as, imagine I draw uniformly randomly from the input space. I run it through the channel I'm interested in, and then I ask someone to guess a value x hat, and I say you win as long as x hat isn't what I actually put into the channel. Which is, instead of like state discrimination, it's like state exclusion. You're trying to guess the wrong thing. And then you can just prove, like just sort of thinking about this, you can see that the optimal winning probability of this game is just rescaling by the input dimension, this quantum Doeblin coefficient. So this is capturing this sort of structure. And so then we can just induce this into the quantum setting in sort of the normal way that we consider classical communication, where we introduce an encoder, which is this EMAP, and a decoder, which is guessing the x hat. And then this whole thing with the quantum channel and we're interested in is a classical channel, and so we can talk about the induced Doeblin coefficient, which has to do with this game, which is just infamizing over all the possible Doeblin coefficients we can induce by a given quantum channel. Yeah? So we can also do one further step in sort of the same way we have classical capacity of a quantum channel. We can go to the entanglement-assisted Doeblin coefficient, or this noisy state exclusion game. So here we have an entanglement assistance, which is this pure state. Then you still encode, and then you have a decoder, which now has this extra reference system. And so we can, in fact, do this a little more generally. We can imagine that the decoder is constrained to some cone k. And so this gives us a whole family of induced Doeblin coefficients. And so really the critical point, and the only thing I really want you to take away from this sort of unification, is in the case where I consider the induced Doeblin coefficient, but I allow for arbitrary entanglement assistance, we get the quantum Doeblin coefficient with the positive semi-definite ordering we saw earlier. And if we consider the separable cone, so you have entanglement breaking on the decoder, then you get the quantum Doeblin coefficient introduced by Wolf, which has this separable ordering. And so this, really all this is saying is that we have this unified picture of these quantum Doeblin coefficients in terms of the strength of the decoder. That's the idea, where we have entanglement assistance and then we interpolate by the decoder strength. And so this unifies these. Okay, so that covers sort of giving us an operational picture of all of this. We have further interpretations. There's a whole set of them. The one I really want to highlight for the rest of this talk is the reverse robustness, because we'll use this to address the second question about this complete contraction coefficients. And what this is saying is I can decompose the quantum channel I'm interested in into a convex combination of another channel and then a replacer channel that prepares something in the affine Hall of the density matrices, which is a little weird from a physical perspective, but from a mathematical perspective will work well. So that's what we're doing here. Okay, so we have an operational interpretation. We have all these other mathematical representations. It's, I think, reasonable at this point to ask what makes the quantum Doeblin special. And I want to stress that I think this is a reasonable question because we saw that we had this hierarchy, and we know that the trace distance is upper bounded by this previous Doeblin coefficient. So what makes the one that's not tilde useful? What makes it special? What selects for it, right? And I think we can sort of guess this from the operational interpretation that we saw earlier, because we already saw that we have this sort of noisy state exclusion game where in one case we have entanglement assistance and in the other case we don't. And so this might suggest to us that what this quantum Doeblin coefficient is capturing is something that has to do with entanglement assistance or a reference system. That's just an intuition, but that's sort of the idea. And so from that, we can motivate complete contraction coefficients. So what is a complete contraction coefficient? Let's start by defining them for a fixed R. So here, instead of just considering two arbitrary inputs on the space of the channel, which is what we saw at the beginning of the talk, we now have a reference system. The only thing is we have to require that the reference systems have a fixed marginal. The reason for that, right, is if I gave you different marginals, then I could add a flag state and it wouldn't measure any sort of notion of losing information because just the reference system carries the information. So we supremize over all states where they have the same fixed reference marginal and look at how much information is lost according to the channel necessitance. And then we can supremize over the choice of the dimension of R. So this is a complete contraction coefficient, and it sort of fits in the way that we think of, completely bounded norms or something, in the sense that we have this sort of stabilization in terms of identity, and then we supremize over the reference system. Yeah? And again, Gao and Roger had introduced this idea of a complete contraction coefficient for the case of the relative entropy, but here we're really looking at it first here for arbitrary divergences, but then we'll really look at it for the trace distance. And two things to highlight, I think, about these in general is first, they can only upper bound the normal contraction coefficient, so whatever they're capturing, again, is something stronger. And second, they still have this multiplicativity over composition property that we want. And the reason we want this, right, is because our motivation is to sort of peel off these layers of this circuit, so we really need this sort of structure. Yeah? Okay, so this is the fundamental relation that gives us that the quantum Doeblin coefficient is special, I would say, which is that the complete contraction coefficient is upper bounded by 1 minus the quantum Doeblin coefficient. And this is a super simple proof, and I think it's fun, so I'm just going to present it in case maybe it's useful for other people when they use sort of these robustness ideas. Yeah, okay, so we start with two states, arbitrary AR sigma R, where they have the same reference marginal, because remember that's what we care about for contraction coefficients. Then we take this reverse robustness idea that I introduced earlier, so we've decomposed our channel in this way. And then we can just look at originally how the thing we're interested in, which is the difference between the states under this channel. But then I can apply the reverse robustness so that I've got this replacer channel and some other CPTP map. And then the replacer channel is just going to prepare this tau A on both of these states, regardless of if it's rho or sigma. And since they have the same marginal, this part goes away. So we go back to somehow the part where we actually have a CPTP map and everything looks sort of standard physical quantum. And then we can just use the data processing inequality to get rid of that channel. And so if you divide by 2 and reorder things, we get the relation in terms of the contraction coefficient that we want. So this is really what's going on here. Okay, so at this point, we have this unified picture. We have a bound on the complete contraction coefficient. Again, I want to stress that this is efficient to compute because it's an SDP. So that's sort of the operational, or the application advantage. But we still have one missing picture, which is, if I go back to the circuit problem that we're interested in, peeling off these layers, I might want to be able to keep track of the fact that I know some extra structure on the gates at a given layer. And so what I really like is that the Doeblin coefficient, say for layer 2, which I know is actually the tensor product of these two channels, decomposes. But all we get is submultiplicativity. And in fact, this is can be strict. And so we really are stuck with this issue that it's submultiplicative, and so we can't peel things off quite as cleanly as we want. So what we introduce is the Doeblin-Wang SDP, which is like the quantum Doeblin coefficient SDP, except we've added this lower bound in terms of the negative. And the reason we call it the alpha Wang is after Professor Wang, because he uses this idea of getting multiplicativity from introducing these upper and lower bounds, I guess, frequently. And so, indeed, using this sort of idea, we get that the alpha Wang is multiplicative. So this is really nice, because now we can address these sort of circuits. So we go back to this idea where we have the circuit and we have the ancillary registers, which means that which is relevant because we want to think about complete contraction coefficient. And we can really just peel things off, right? So we start with the complete contraction coefficient peeling off in the way that we wanted earlier by the multiplicativity. Then we have the inputs, which are distinguishable under trace distance, but this is just going to be less than or equal to 1. So really all we care about at this point is calculating these complete contraction coefficients. Yeah? And then we can take a given layer and we can decompose it or upper bound it in terms of 1 minus the alpha Wang, and then we can use the multiplicativity to peel apart each layer into its given channels. And so we've got this really clean framework for decomposing everything so that we can actually calculate things. That's the idea. Okay, so now that we have all the tools we want, we can look at applications of this. So the first application we'll consider is noise-induced barren plateaus. Just as a reminder of how noise-induced barren plateaus work, you have a variational quantum algorithm, which means that you've got a classical computer that's hooked up to a parameterized quantum circuit that's supposed to help you sort of traverse the cost function of something that has to do with those parameters. So the idea is that each time you run the circuit, you get some information about the cost function, which allows you to update the parameters in your circuit. And the problem of noise-induced barren plateaus, which was addressed first by this paper by Wang et al. In 2021, is that you imagine that your parameterized circuit between each part of the parameters has some noise. And so the concern is that this noise is going to really mess with your optimization because your cost function, let's say, is just measuring some observable after running this circuit. And the concern is that the noise is going to sort of kill the gradients of your cost function. And so instead of having a nice, strong, like steep descent, you wind up in a barren plateau. So this is the concern, and this was first observed for qubit depolarizing noise in Wang et al., and then it's been shown for trace distance contraction coefficient being strictly less than 1, and assuming the gradient is computed with the parameter shift rule in Schumann et al. Last year, and random circuits with qubit noise by Mellon et al. Also last year. So what we're trying to do is we're building up sort of under what conditions does noise-induced barren plateaus show up. And so our contribution here is we're saying any noise structure and gradient method, so we don't care about those, as long as the quantum Doeblin coefficient is strictly greater than 0. And even in this setting, even if I give you some noiseless subsystems, because we're considering this complete contraction coefficient, you still get noise-induced barren plateaus. So this is like, I guess, an even more negative result on the terms of how noise works. And so our basic setup is that we've got the circuit parameterized with some noise model. We have the same cost function, but now the observable also gets some noiseless ancillary registers. And what we get is that if I fix an I in this step, so capital B is the depth of the circuit, and we assume some basic things about the unitaries, then we get that changing one of the parameters changes the gradient in a way that exponentially gets suppressed in the remaining depth in terms of the quantum Doeblin coefficient. And I was asked to stress that this 2/3 can go away if we assume parameter shift rule. In other certain situations, we can get rid of the 2.1 or tighten it. But I think the key structural point is that in these sort of protocols, you get a decrease that's exponential in the Doeblin coefficient. And I guess I should note that the way we prove this is we take this bound from the gradient from the Melee et al. Paper, and then we use Holder's inequality in our structure of the complete contraction coefficient to get it. So that really using the structure of the complete contraction coefficient is where this comes from. The second application is error mitigation, which Professor Chitagi et al. Have considered. And the idea is you have a set of states that you want to understand the expectations of. So you have some set of states, you have some set of observables for those states, and you want a protocol that for each observable you pick, you would like it that this estimator that comes out of your protocol and uses many copies of that given state can, in fact, guess the observable to appropriate parameter. So we say an estimation protocol is epsilon delta good if the distance from the observable and the estimator being further than epsilon happens with low probability, with less than delta. And so what we show is if you assume that your noise model, again, is this sort of depth circuit, and you have this idea of this measure of the difference between observables for pairs of states, and there's a sufficiently distinct pair of states, right, because you want to do these estimations for different different states, then an epsilon good, delta good estimation protocol requires that the number of copies of states that you are given scales in this way, where, again, what I really want to highlight is that you get this exponential suppression in the depth of your circuit. Yeah? So it's another way of saying that. And just to compare to the previous work, so in the previous work you have the same sort of setup, but here you have to consider minimizing over all your families of channels and looking at the relative entropy. So here what we're getting that's stronger is this this depth claim, and also I think it's probably in general easier to compute these Doeblin coefficients than run through all these relative entropy calculations. But that's less critical. Okay, so I guess just as a final thing, you could ask like why is this enough for all these setups? And the reason is basically that what's happening in all these contraction coefficient settings is that the two states are becoming less discriminable, and so we can actually capture what exactly a complete contraction coefficient is capturing in this way. So I give you two possible quantum states, rho or sigma. They have some R register, and I run the A part through a series of channels, right? And then we can take the Hallego-Hellstrom theorem, which tells us that our ability to discriminate them is in terms of the trace distance. And, oh, right, and I can just call them a whole state G. And if I take the Hallego-Hellstrom theorem, then really what's going on is I'm just saying that the trace distance part exponentially suppresses in the speed of the Doeblin coefficient. Yeah? And so really what's happening in all these things where we're saying it's harder is we're saying the states have just become harder to distinguish. But the key point actually I'd say about complete contraction coefficient is it's saying not only that, but also the extra ancillary register that you saw earlier, it's becoming decoupled. It's becoming irrelevant to what went in. And so we can actually sort of extend this idea of mixing times, where now if I have, let's say all these channels are the same and they have some fixed point omega, then we can say that actually for any state, even if I give you this extra information, as I run it multiple times, I can calculate how fast it goes to being independent as a function of the Doeblin coefficient. So we can think of this as a decoupling time, which generalizes the notion of mixing time. Okay, so just to recap, we started by studying the framework of quantum Doeblin coefficients, where we established properties and operational associations, like this reverse robustness idea, and also this coding argument in terms of noisy state exclusion. Then we established the first efficiently computable complete contraction coefficient, which is what makes this one quantum Doeblin coefficient so special. And then we use this to generalize the limits of noisy quantum information processing via the quantum Doeblin coefficients. So the ones I talked about was the noise-induced barren plateaus and error mitigation, but also in the paper we look at noisy hypothesis testing, sample complexity, fairness in quantum machine learning, and then the decoupling and mixing time. So thank you for listening.
All right. All right. There's already questions. Thanks, Ian, for a very nice talk. Actually, there's some back there. Who's first? Yeah, let's get Eric.
Thank you for the talk. I have a question about the multiplicativity.
Yeah.
So do you have examples, like explicit examples, when you don't have the multiplicativity?
Yeah.
And then also the second part of the question is for the entanglement assisted case, then do you restore multiplicativity?
No, no, good question. Yeah, so this makes it very different than the communication. So for not having multiplicativity, it actually suffices to have a classical to quantum channel with qubits. And there you can get it so that the Doeblin coefficient of a single copy is non-trivial, but if you tensor it together, actually the Doeblin coefficient is 0. So it's really strongly sub-multiplicative. And then the second question was the entanglement assistance, but the entanglement assistance does correspond to the normal Doeblin coefficient, like what we call the quantum Doeblin coefficient. So that's an example of it not returning in that setting.
Okay, yeah.
Follow-up question to that. Do you have any classes of channels for which it is multiplicative?
Classical channels, I believe. Like literal classical to classical channels.
Okay.
And then I think quantum to classical channels as well.
And any relation to capacities?
I didn't think about that. I don't know, Christoph, did you think about relations to capacity?
I guess think it's an upper bound, not very good. I don't think that direction.
Because it's like stated exclusion and not really actual classical information.
Yeah. Can I ask a question about this alpha 1 quantity?
Yeah.
Can you go to that slide? Okay. For what type of channel you know this one can gives you non-trivial contraction?
I don't know if we looked into it that much. I mean, that shouldn't really be the barrier though, right? Because it's not like it's additive. Like it's still, since you have this 1 minus the multiplicative part,
Yeah.
it's still going to, like if I give you more and more copies, it's still going to go to 0. So which is what you want, right? Because that's saying that quantum error correction exists.
But you show that this one is multiplicative, right? So, okay, but you have 1 minus this quantity.
Yeah.
Which also will decay if you do.
Right. It will decay towards 1, which is like saying that you can do error correction.
So in general, you cannot do tensor stable estimates for the coefficient.
Yeah, but I mean, you know that you can, right?
Yeah. Okay.
That shouldn't work.
Yeah. Okay. Thanks. Yeah.
Any other questions? Omar.
Thanks a lot for the talk. Yeah, there is another quantity. I'm not sure if it can be called quantum Doeblin coefficient, but which is multiplicative and efficiently computable. It's the minimal eigenvalue of the choice state of the adjoint of the channel composed with the channel itself. I don't. Okay, it's a bit complicated, but it's in Michael Wolff's notes. I don't know if you know this, or so it's multiplicative and additive. Multiplicative and efficiently computable. So do you know how it is linked to this alpha plus?
I can take a guess, but it's so in the classical case. So the reason I'm thinking of this is the quantum chi squared input dependent will be the channel and its adjoint second eigenvalue, which is in a different paper.
Okay.
And so what you're describing, I think, should be lower than that. So I think it should be like the exact opposite on the spectrum of contraction coefficients in some sense. So yeah, but I don't know how to prove that without some technical argument.
Okay, thanks.
Yeah.
Yes, absolutely.
I hadn't thought about that, but that should make sense because we know the zero error capacity relates to the contraction coefficient of trace distance in the classical setting. And since this is upper bounding that, there should be some connection, but it shouldn't be direct. Or like, take a look at that.
Any other questions? Well, if not, let's thank Ian again.